Thanks, Sergey, for the introduction. And let me also thank all the organizers for the effort in putting this conference together. It's really, really nice to be here. And thanks for the chance to speak here to you today. So I'm Massimiliano Rossi. I'm a postdoc in the Photonics lab of ETH Zurich. And today I want to tell you about some recent experiments we have done in the lab about how to control the motion of a levitated particle in a cryogenic environment at the quantum level. And I want to start emphasizing actually the importance of mechanical systems in science and technology today. And this lies in also in the major advances that the field of cavity optomechanics has seen in the last decades. And in this field now, we managed to have incredible control of this mechanical motion via some electromagnetic readout. And we have also actually heard a very nice example from Eva about that. And also in cavity optomechanics, using mechanical systems, different groups in the world have done incredible tests and quantum mechanical experiments using macroscopic systems. Now, on the other hand, mechanical systems are also pretty important for technological applications. And an example is using mechanical systems for ultra precise sensings. And that's because actually the displacement of these objects can be used as a transducer, as a pretty universal transducer to other forces. And an example of such a precise sensor is given by a gravitational wave detector, where the mechanical resonator is a kilogram mass, which transduces a gravitational force into a displacement. Now, on the other somehow end of this scale, there are systems, mechanical systems, which are levitated, and levitated optomechanical systems are actually very nice, and they actually offer unique features compared to other experiments, in particular because we have full control of the mechanical potential. And this is a really interesting platform to, for example, if you want to test fundamental physics. And this is actually the topic of my talk today. So I have three parts for my talk. I will start giving you a brief introduction about what levitated optomechanics is and how to use this platform to do a displacement measurement. Then I'll move on to describe you the experiment we've done in the lab, where we have achieved a quantum control of this displacement. And at the end, I want to give you some future views of what comes next in the lab, and I want to dream a little bit with you about future experiments. So let's get started with a brief introduction. Now, in levitated optomechanics, one of the two central parts is the levitation, and the levitation is offered by an optical tweezer. So we take some laser field, we strongly focus this field down to a diffraction limited spot, and this is an optical trap. Now, it's known since the 70s, since the pioneering works of Arthur Ashkin and colleagues, that if we now take a dielectric object and send it through this diffraction limited spot, this object will experience a restoring force towards the maximum of the optical intensity. So this force is sometimes called the gradient force, and forms confining potential for this dielectric object here. So this object is the mechanical system we want to study, and to first order, it behaves as a mechanical oscillator. So the potential energy is a quadratic energy. And now this dielectric object, in the limit where the dimension is much smaller than the wavelength of the laser, it behaves as a dipole. And as any dipole, it will scatter the trapping field around. And so we have some scattered field, and this is the basic of the optomechanical interaction which is going on in this experiment. And this is a standard optomechanical interaction. And just to tell you how it works, on the one hand, we have the radiation pressure of the trapping field, which exerts a force on the mechanical resonator. So this object, this particle moves, but as it moves in this trap, it will also change the phase of the scattered field. So this mechanical information, or this mechanical displacement, is now encoded in the phase of the scattered field. And if we measure this phase interferometrically, for example, then we can perform a continuous displacement measurement of this object. Now, in any measurement, actually, if you want to quantify the strength of this measurement and efficiency, then there are two quantities that we have to understand. One of these quantities, the so-called measurement rate. The measurement rate tells you how fast the interferometric measurement can extract or can resolve a given displacement, which is the 0-point fluctuations. That's the residual motion when this particle is in the ground state of the harmonic potential. Now, this measurement rate depends on few experimental quantities. On the one hand, it depends on the amount of scattered power by this particle. So the more power we scatter, the faster we can measure this motion. And it also depends on the efficiency with which we record this phase information. Now, on the other hand, we have to compare this rate to the so-called total decoherence rate. This rate tells you how fast the motion of the particle is disturbed by the environment and the measurement itself. So there are actually several contributions to this decoherence rate. Maybe the most important one is the so-called quantum backaction. The quantum backaction is the disturbance predicted by the quantum theory because of the measurement action itself. So since we are learning some information about displacement, then we have to perturb, we have to disturb the momentum of this particle. And in the context of levitated optomechanics, this disturbance occur because of recoil of this particle due to scattering of photons. Then we also have actually other classical decoherence mechanisms that we have to take into account. And maybe the most important one is the decoherence due to collisions of the molecules of the gas surrounding the particle with the particle itself. But nevertheless, these two quantities are the two important quantities in the measurements. And a very important figure of merit for a measurement is given by the so-called measurement efficiency, which is the ratio of measurement rate to total decoherence rate. Now, this measurement efficiency, as the name suggests, is upper bounded by 1. And this one is actually a consequence, this bound is a consequence of quantum mechanics. And this is sometimes called the Heisenberg measurement disturbance relation. And that's an important bound because it also allows us to define the regime where quantum effects of the measurement becomes important. And this regime is given by this efficiency close to 1. That's where we should be able to exert a measurement-based quantum control on the motion of this particle here. Now, so that's the overview of the system we are using in the lab. Let's move on now to see what we are actually doing. And let me give you, or let me tell you some more details about our experimental setup. So I already talked about the optical trap itself, the optical tweezer. Now the object we study is a silicon nanosphere with a diameter of 100 nanometers. So we trap it in this optical tweezer. The diameter, as I told you, is much smaller than the wavelengths. We use a telecom laser. And also in the following, I will focus on the motion of this particle along the optical axis, which I call Z. Now, to achieve a large measurement efficiency, we need to maximize the quantum backaction over the excess decoherence. And to do that, we now place this optical trap in a cryostat, which reaches something like 60 Kelvin. And this is helpful because the cryogenic pumping mechanism allows us to enter a ultra high vacuum regime for this experiment. So we measure our pressure is below 10 to the minus 9 millibar. And this essentially makes the gas collisions very rare to occur. So, and the quantum backaction is the dominating source of decoherence. Now, on the other end, we also need to maximize our measurement rate. And to do that, then we have to collect all the information about the mechanical displacement. And to do that, we also have to recognize that as this particle moves along the optical axis, actually, most of this information is encoded in the phase of the backscattered field into this trapping lens. So we actually collect this backscattered field, and we send most of this light, actually 90% of that, to a homodyne detector. And we stabilize this interferometer to record the phase fluctuations of the scattered field. So this is our measurement, and we do that with a large efficiency. Now, so now we have recorded this phase fluctuation in an electrical signal, and to analyze them, we can now look at the power spectral density of the photocurrent here. And if we do that, what we observe is the following spectrum, these dark red trace. And so this is a spectrum in displacement units as a function of frequencies. And now we can model this as a Lorentzian function you see here, which is centered at around 77 kilohertz, which is the resonance frequency of our mechanical resonator. And we can actually from this spectrum we can extract the two important quantities, the two rates for characterizing the measurement. In fact, this background here, this tells us what is the imprecision of our measurement. So what's the displacement we can resolve? And in fact, it is inversely proportional to the measurement rate. So directly from this background, we can extract a measurement rate of around a kilohertz. Now, what about the decoherence rate? Well, the decoherence rate is the responsible of the fluctuations of this displacement. And we can extract this amount of fluctuations from the area under this Lorentzian function. And also the rate at which this fluctuation enters, we can extract it from the line width. So from these two information, we extract a total decoherence rate of around 5 kilohertz. And now by comparing these two numbers, we extract for our system a measurement efficiency of 24%, which is very close to 1, meaning that now we should be able to perform some kind of quantum control on this nanosphere in this optical trap. Now, what is the kind of control we want to achieve here? Well, we have now, let's think a bit more about our measurements and the effects of our measurements. So as I told you, the main source of decoherence is the quantum backaction. Simply because we are measuring, we are disturbing this motion here. At the same time, these fluctuations, we record them very precisely in this detector. So now we have these fluctuations recorded in a photocurrent. And the idea is that the idea is to use these fluctuations to counteract for the idea is to use this photocurrent to counteract for the fluctuations of these particles. So we want to remove fluctuations as much as possible, and ideally we want to cool this motion down to the lowest energetic state allowed by physics, by quantum physics. That is the quantum ground state. And this measurement-based control is sometimes called a feedback cooling. That's actually a pretty well-known technique in the context of mechanical systems and optomechanical systems, as the rich literature witnesses. Now, when this feedback cooling scheme is based on a quantum measurement, as the one I just showed you before in the previous slide, then it becomes essentially an example of a measurement-based quantum control. Now, what's the idea? How to remove these fluctuations? The idea is to actually introduce another force on this particle, which is a damping force, to damp this motion out without, however, introducing any fluctuations, or actually with introducing only a quantum limited amount of fluctuations. And this is sometimes called the cold damping approach. Now, if you want to add this damping force, then we need to, from our displacement measurement, then we need to estimate the velocity of the particle in order to generate a viscous force. And to do this, we have to process the photocurrent, and we do that electronically with some digital filter here. We actually choose a simple delay line. So we take our measurement, our displacement measurement Z, and we delay it by 1/4 of the mechanical period. And here we now rely on the harmonic evolution to rotate displacement into velocity. So we then invert this velocity, and finally we actuate this force by a Coulomb interaction. So we simply apply this voltage to 2 electrodes surrounding our particle, which is actually electrically charged. So that's our Coulomb interaction. So in this way, we generate a feedback loop to control the motion of this particle. Now, what we can do, we can now look at the, again, at the spectrum of this photocurrent, of this homodyne photocurrent, as we increase this electronic gain. So, and again, we start from our initial spectrum, as I showed you before. We can feed this spectrum to a model from which we can actually extract the average mechanical energy, which I show in this right plot. And this energy is now in units of phonons, so mechanical quanta. And we start at something like 200 phonons or so. Now, as we increase the feedback gain, we can record the spectra. And what we see, we can actually notice 2 things. The first thing to notice is that as we increase this, the strength of this damping force, the line width of the spectrum increases. So this is a signature that we have more dissipation in our system. But the second thing we have to notice is that the area under each of these peaks does not increase or actually reduces as we increase the electronic gain. And this is also shown in this plot where we plot the average energy as a function of the induced dissipation rate. So you see that we're actually removing energy from the system. We're cooling it down. Now we can keep increasing the feedback gain, and what we will find is a spectrum which looks essentially flat. So this actually does not mean that there is no more motion, but this is actually an effect of correlations present inside the loop, sometimes called noise quotient. But nevertheless, we can model these correlations. We can fit this spectrum from which we can actually extract our lowest occupation of only 0.65 phonons, which is well below 1 phonon within the uncertainty of our measurements, meaning that this particle has been cooled to its quantum ground state, essentially. Now we can also compare to what is the limit of this feedback. And the limit is actually given by how well we can estimate our conditional state. And again, this is simply given by the measurement efficiency. So if we plug in our number, we find that the optimal cooling would bring us down to only alpha phonons, which is actually pretty close to what we get. Now, but as I told you, this actually relies, this estimation relies on fitting some in-loop dynamics. But to corroborate this result, we can also now perform thermometry measurements by extracting part of the scattered light outside of the feedback loop. And we analyze this light with a heterodyne detector. So we take again the photocurrent here, we compute the power spectral density. And now, if we look at the power spectral density, we will actually observe 2 sidebands at plus and minus the mechanical resonance frequencies. So we actually interpret these sidebands as a result of a Raman scattering process between the photons of this trapping field and the mechanical motion. And now one of the sidebands actually reflects the absorption of photons, whereas the other sideband reflects the emission of photons in these scattering processes. And actually, we can see that these 2 sidebands differ in the amount of power they carry. And this difference, this asymmetry, is actually due to the 0-point fluctuations. That's an intrinsic quantum mechanical difference, in which we can actually use to calibrate the power itself in units of mechanical quanta. We can also extract a similar, we can perform a similar thermometry if we look now at the correlations between these two sidebands. So we can calculate the cross correlator, and now the imaginary part of these correlations, this asymmetric line shape, is again the motion induced by the 0-point fluctuations, independent of the mechanical occupation, whereas the real part is proportional to the average energy. So we can use this imaginary part to calibrate the area under this real part and extract the occupation. And from these two methods, we can extract again an occupation of 0.65 phonons, corroborating the results that we managed to cool this particle down to its quantum ground state. And this is actually the first time that a levitated system that one has performed a measurement-based quantum control of a levitated system. I also want to mention that actually there is also another recent work done by an independent group which has shown similar results to our. That's the work of Lorenzo Magrini and collaborators in the group of Markus Aspelmayer in Vienna. And if you are interested, check it out on the archive. So now let me jump into the last part of my talk where I want to give you some perspective for what comes next. Now, one thing which I didn't highlight so far is that our optomechanical system can now achieve this quantum control without the use of an optical cavity. And this has some advantages because it allows us to overcome some of the instabilities typical of an optomechanical cavity. In particular, one of these instability precludes to have measurement speed larger than the mechanical period. So we can now think about going in this new regime. We can increase the speed of our measurement and we can make it faster than the mechanical period. And what we could get is a projective measurement. So to understand that, we can now think at the phase space of this mechanical resonator. So we have seen this, Eva has introduced this phase space in the previous talk. So we know that if we have a mechanical state, the harmonic evolution will make this state rotating in phase space at omega m, at the resonance frequency. However, now, if our measurement rate exceeds this mechanical resonance frequency, then essentially the measurement happens much faster than any harmonic evolution. So we can consider our state frozen in the phase space. And what the measurement does, it simply reduces the imprecision along the position axis, of course, at the cost of increasing the uncertainty in the momentum axis. That's the quantum back action. But you see now that this approach is a projective measurement, and that's actually an interesting route to explore if you want to generate a mechanical squeeze state simply by measuring it. And that's also an important tool if you want to perform a state tomography of a mechanical system. So the other perspective, the other interesting direction, and now we can dream a little bit, regards the generation of macroscopic quantum states. Now, if we go back to our system, what I told you essentially is that as of today in the lab, we can generate a quantum ground state of this nanosphere here. And the ground state is actually a pure quantum state. So if you think about the wave function, this wave function is a Gaussian function, which is actually well localized in space. So if we compute it for our particle, we find that the width or the size of this wave function is around 10 picometer, so much smaller than the particle size. Now, if you want to generate a macroscopic quantum states, somehow we would like to expand this wave function to a size which is comparable to, or actually even larger than, the diameter of the nanosphere itself. And that's where the unique feature of levitated systems comes into play. Because to do this expansion, what we can do now, we can simply switch off our optical trap. So that's a unique feature of all levitated systems. And if we do that, what we have is a nanoparticle in a quantum state which undergoes free evolution. And as we know from quantum mechanics textbook, this wave function here will now broaden, will expand in space. Now, if we let enough time for this expansion to happen, now we can envision that we can generate such a state where this wave function is larger than the particle itself, meaning that the center of mass of this particle is now delocalized to within a range larger than the object itself. And that's a pretty interesting regime for studying macroscopic effects of quantum mechanics. Now, the catch, the problem of this experiment is that this expansion should happen without any decoherence. So we need to have a long coherence time to allow this wave function to expand. And once we switch off the optical trap, there are two main sources of decoherence we have to avoid. So the first one is, again, collisions of this particle with gas molecules. And in fact, every time a molecule from the surrounding gas collides with the particle, it localizes the particle itself. So the wave function collapses. And we want to avoid that. And to do that, then we need to operate the system in an extreme high vacuum environment. On the other end, this nanoparticle is a black body. And as any other black body, it emits photons. And these photons, so from the emissions of these photons, they carry information about where the particle was at the moment of the emission. And that's, again, another decoherence mechanism we want to avoid. Now, because of this, so the optical trap requires high optical intensity, meaning that the internal temperature of this particle is usually increased to hundreds of Kelvin. So to avoid this black body decoherence, then we need to reduce the internal temperature of this particle. Now, and to achieve these two, or to meet these two requirements, what we need then to do, we need to operate actually this system in a cryogenic environment. And that's the strength of our system, which already operates in this cryogenic environment. Now, what are just to give you some numbers, what are the pressure and temperature we need to achieve? Well, if we want to expand the wave function up to 100 nanometer, then we need to have roughly 50 milliseconds of coherence time, which requires a pressure of the order of 10 to the minus 12 millibar, and a bulk temperature of the particle of around 60 Kelvin. And that's actually already the temperature of the cryogenic environment we are working with. And this pressure is actually within the reach of cryostats. So we are confident that in the future, not so far future, we can meet these requirements and start to generate these macroscopic quantum states. Okay, so that's the end of my talk. Before concluding, I want to acknowledge the other people involved in the experiment, in particular Maria Luisa and Felix, and also Martin and Lucas, and of course all the funding agencies. And I conclude with this summary slide, and I'm happy to take any questions. Thank you.
Thank you very much, Massimiliano. Very interesting talk. Again, I'll do the best imitation of the big audience here. I can see the comments and questions. So let me get to it from Uros Delik. Cool results. How well do you cool of other two oscillation axes? Is that enough to prevent particle escape along other axes during the free fall?
Yes, so at the moment, we have two additional feedback loops to reduce the energy of the transverse modes. I don't have like numbers for the phonon occupation of these two modes. It's something around hundreds of phonons. For the future experiments where we want to do this free fall, then we will also need to have actually some other trapping mechanism to avoid also like gravitational fall of this particle. So we're planning to use a purely electrical trap, not an optical trap. And there we will, the plan is to also apply some kind of, to always keep some kind of feedback loop on the transverse modes based on this electrical trap.
Okay, so another question, well, actually there are three questions, but it's from Jiangxian Chen. Brilliant work. Why is the starting phonon number only around 200?
Yeah, that's a good question. So we have to. So since the dissipation rate due to collision with the gas molecules is of the order of milliards or even lower, and since we're in this optical trap, we need to always apply some feedback cooling to this particle to avoid losing the particle. So we want to reduce the average energy, otherwise this particle will, you know, it's highly probable that this particle will fall out of the optical trap, which is not really deep. And so these 200 phonons I show you, this is the, you know, the initial feedback we apply to simply stabilize the particle.
Okay, I will also ask the second question from Jinseng Chen. Romero Isart proposed a reverse potential evolution. Is there any way to implement this?
Yeah, that's also, so to implement that, the idea will be to, again, have an electrical trap, a pole trap, and to invert the potential of that electrical trap. So this has to be done to in a non-optical trap to avoid decoherence of quantum back action, essentially. And that's this reverse potential is to make the free evolution faster, essentially to expand the wave function faster.
Okay, I will also go then to the third question because it seems to be short. In UHV experiments, how does temperature of the cryostat correspond to particle temperature?
Yes, so if you have an optical trap on, then essentially the optical trap will heat up the internal temperature of the particle, and that's to something like 500, 600, 700 Kelvin, and the particle will not thermalize to the cryostat temperature. However, once you switch off the optical trap, your particle will thermalize. So because it's a black body, it will thermalize. It will emit photons to thermalize to the surrounding environment. And for silica nanospheres, you know, this thermalization happens over, you know, something like 100 of milliseconds. And, you know, without absorption of optical radiation, you will, the particle will thermalize to the temperature of the surrounding gas, which is given by the cryostat temperature.
Okay, great. Thank you, Massimiliano, for a great talk and answering questions. I would like just to mention that there is another more like a comment and also interesting question in the chat that you can consider answering via email.
Yeah.
But since we don't have time for that, I'd like to go for the next talk, and that would be
thank you.
Given by Juros Gelik from University of Vienna. And the talk title is Quantum Control of Levitated Nanoparticles. Please.
Okay, now you hear me, I guess. Okay. So yeah, hi. So the talk title is quite similar to Massimiliano's title. It's about quantum control of levitated nanoparticles. My name is Uroš Delić. I'm a postdoc in the group of Marcus Aspelmeyer at the University of Vienna. And I just like to put an emphasis that here it's going to be a talk that actually has optical cavity inside. So we are using cavity optomechanics to cool the motion of our levitated nanospheres. To start with, I just want to go quickly over the concept of optical levitation. So one can talk about optical levitation as through the Hamiltonian of the interaction, which is typically typically written in the form of the dipole interaction with a light field. So whenever you actually have a focused Gaussian beam, you can create something like a 3D harmonic potential for the electric nanoparticles. In our case, as you can see, we have a microscope objective with a waist of something like 700 nanometer. And we try to trap nanoparticles that have roughly 10 times smaller size of 17 nanometer. This is purely a concept that has been devised in the group of Arthur Ashkin 40 and more years ago. So, of course, then if you actually have, your harmonic oscillator, then in addition, you will also have, for example, decoherence, and some of the possible decoherence mechanisms that you can have is through the collisions with the gas or by the photon recoil of the optical trap that you have. And for example, if you try to measure the motion of these nanoparticles, you would get something like an oscillating time trace that you see in the upper right corner. And ideally, we like to see the statistical properties of this motion. So what we do is we plot a Fourier transform of the power specular density that gives us information about the central frequency of the oscillation, about the line width of the oscillation, and the area below the peak corresponds to the energy of the oscillation or the variance. Already in his seminal work in PRL in 1970, Arthur Ashkin said that the extension to vacuum of the present experiments on particle trapping in potential wells would be of interest, since then any motions are frictionless. And you can see that actually in these examples of the motion at almost atmospheric pressures down all the way to high vacuum, where you go from a highly overdamped harmonic oscillator to a nicely underdamped harmonic oscillator, and you can actually measure quality factors up to 10 to the 8 or higher, depending if you have ultra high vacuum pressure. So you can actually see that your system is suitable for quantum experiments at room temperature. And this is what got us interested in running the system. However, in the recent years, there has been kind of a shift of interest into experiments with levitated nanoparticles. I'd like to just point to two different works here, both from the group of Romero Isart. On the left side, so you can see that, for example, free-fall experiments would be feasible, where you could actually probe decoherence mechanisms, or it actually involves it allows for long expansion times, so something that Massimiliano was also talking about. While on the recent work, for example, you can apply inverted potential. So this is something that optical levitation can do compared to other optomechanical systems. And you can speed up wave packet expansion, or if you have some higher order nonlinearities, you can try to create non-Gaussian states of matter. And so I will just focus here on 3 different points in my talk. I will briefly go over the previous work a couple of years ago, where we combined optical cavity with an optical tweezer, and show some previous results on dispersive coupling. However, I will mostly talk about the shift in paradigm in these cavity optomechanical systems to coherent scattering schemes, which in the end allowed for 1D ground state cooling. And as an outlook of this talk, I will present our recent efforts toward reaching the full quantum control via ultrastrong coupling with the cavity field. So just quickly over integration with an optical cavity, typical problem in optical levitation setups with cavities is that if you have many particles flying around your vacuum chamber, they're big, so they can stick actually to cavity mirrors and ruin your cavity finesse. So this is why we made a modular setup where the cavity is completely separate from the optical levitation part. And the first problem that we encountered is, of course, the typical microscope objectives that you get have short working distance, so it's really hard to fit a nanoparticle on the cavity axis. Seems like a postal problem that we typically encounter. So how we solve that is we cut our cavity mirrors to thin strips, and now we are able to place the nanoparticle on the cavity axis and move it around with quite some flexibility. How our setup actually operates is you have a microscope objective only, and then you trap a nanoparticle, and only then you actually bring the optical cavity into your system. And after that, we of course add also a collecting lens in the tweezer transmission to also monitor the particle position slightly. To show that this is quite a robust setup, this is my colleague, David Gras. This is the vacuum chamber. It's his hand in the vacuum chamber, and this is a particle trapped in a microscope objective, and you will see the two cavity mirrors coming here and there. This is a fully reproducible 100% rate of loading nanoparticles in a high vacuum system, because after this, we are able to pump down to something like 10⁻⁶ or 10⁻⁷ millibar after a day of pumping. With this system, we already managed to probe some dispersive coupling interactions, standard optomechanical Hamiltonian, which in the dipole interaction would look something like this. So you have the particle with polarizability alpha interacting with the intensity of the cavity field. This means if you actually, if the particle moves left and right along the cavity standing wave, you would expect that the best coupling rate is at the cavity intensity slope. This has been proven, so this has been proposed in many papers around the world, and also many experiments were ongoing in the previous years where this type of a coupling scheme was used for cavity cooling. When you have your pump beam of your cavity ready tuned with respect to your cavity mode, you would create Stokes and anti-Stokes sidebands, and if you amplify the anti-Stokes sidebands, you can do cavity cooling of your setup. We showed that we can really nicely position the nanoparticle along the cavity standing wave, so we could optimize the linear coupling, which is the blue line there. We could also see quite significant quadratic coupling terms, and we could, of course, also see a little bit of cubic coupling, so we could see the whole Taylor extension of a sinusoidal cavity standing wave at the end. In addition, we could reach also quite okay coupling rates, even in high vacuum of 10⁻⁶ millibar. However, this didn't allow us to do ground state cooling, and some of the, for example, two limits that one experiences is if you would like to increase the coupling rate, then you increase the intracavity number of photon, but then the cavity pulls the nanoparticle toward the maximum, and your coupling rate deteriorates. Some compensation is possible with a tweezer. This is what we did. However, the coupling rate was severely limited by that. In addition, there was also a recent paper by Nadim Maya from the Roman Kvidan group that nicely shows the limit of laser phase noise to the cavity cooling setups. And this would be technical noise that could be resolved, however, means also a couple of more years of experimental development. In the meantime, we resorted to an alternative strategy, which is in the field of atomic physics called coherent scattering. So what you see there is an SEM picture of our nanoparticle with 70 nanometer radius. And if you have a laser beam driving it from the side and with the polarization coming out of the screen, you can take a picture of the dipole radiation of this nanoparticle. This is an actual picture from our setups in the lab. So you can see that there is a hole in the center where because you're looking along the direction of the polarization, but you can also notice that light is being scattered in the whole circle around the particle in the plane, in the scattering plane. And so far, we've been using our setup like this, where you have a tweezer beam of a completely different frequency with respect to the cavity resonance. However, what one can do is tune the tweezer frequency to be on the cavity resonance, and then you can enhance this coherent scattering. There has been some pioneering work in the group of Blood and Voltage already 20 years ago, some experimental works as well for atoms, and more recently in our group and Lucas Novotny group, we have shown proof of principle that this works, and subsequently we have shown also ground state cooling. How one can, in one slide, describe what is happening is that you have a constructive interference of the dipole radiation where the tweezer photons scattered of the particle can travel both left and right. And there is a resonance condition of the cavity, which can lead to destructive or constructive interference of these scattered photons. If you write it again in the dipole approximation, you now allow also for interference term between the electric field of the tweezer and the electric field of the cavity. We already seen that this first part corresponds to optical trapping, the second part corresponds to standard optomechanics, and the third part is actually what brings coherent scattering into play. If one does a Taylor expansion along the x-axis of the cavity field, one can see that you can get a linear transduction of the particle motion now actually at the intensity minimum of the cavity standing wave, because there the slope of the electric field is the highest. So this is a novel optomechanical coupling that is completely different from the standard optomechanical coupling, which would happen at the slope of the intensity. There's many really advantages of this setup. So for example, as I said, at this point of the standing wave, you have destructive interference of elastically scattered photons, which means that cavity is in principle empty. However, you do have still Stokes and anti-Stokes sidebands because you do have this highest coupling to the motion of the nanoparticle on the cavity wave. However, as there's, again, destructive interference, you don't have any laser phase noise, you don't have no co-trapping with the cavity, you don't have additional recoil heating from the cavity mode, there's no intensity noise, and as the last detection is clean and shot noise limited, because you don't feed all of these noises into your system. In addition, when you have particle in the cavity, the cross-section is given something like radius over the waist square. Here, one of the wastes is changed with the waist of the tweezer, so you actually have a bigger interaction cross-section, so you can increase the coupling rates. And in addition, we have shown also that it is a genuine 3D effect, so you can actually do 3D cavity cooling by coherent scattering. For example, so this is as you can see here, so we have the red and the blue, which is the Stokes and anti-Stokes sideband scattered, and in principle, the elastic scattering should be suppressed fully by the cavity. We have shown also the different periodicity of all of these behavior. So if you look, for example, into the blue line, this is the dispersive coupling to the cavity mode, and you can see that its periodicity is the periodicity of the cavity standing wave. However, the coupling via the coherent scattering, which is the green line, has the periodicity of the electric field of the cavity. So this really proves that it is a different method of coupling. In addition, you have the red line, which is the full Purcell effect enhancement of the coherently scattered light of the elastic scattering. And this also allows for the cooling of the z-axis. As I said, we were able to do 3D cavity cooling. So this is simultaneously showing that the spectrum of all three modes has been decreased for this interaction. How do we go to the cooling of the Y mode, which in principle should be orthogonal to this whole picture? Is we rotate the polarization by 45 degrees in this example. And this brings us a cavity projection of the X and Y motion onto the cavity axis. Z, as I said, can be cooled in a completely different position. So if you actually have if you put the particle somewhere away from the cavity node, it would also allow for some cooling of the Z motion. So you can, in principle, have the 3D cooling of the motion, which allows then also for you to pump down to high vacuum and not to lose the particle in the process. As it turned out, also the X and Y modes are pretty close in frequency space. So there will be some hybridization between these two modes, meaning that the measurement of the occupation will not be also that straightforward. And there has been actually many works on that already 40 years ago. In the ML group, it was noticed that for the ions, in order to be cooled really in 2D, you need to have non-degenerate modes of motion. And recently, we also put on arXiv a theoretical paper that shows what requirements have to be satisfied for really 2D ground state cooling via the cavity, via the coherent scattering. Today, you will also see a poster by Marco Toros on this topic, and I highly suggest, if you're interested, to look into it to understand really what this hybridization will limit the cooling. So to show again the setup itself, as I said, so we have typically the Stokes and anti-Stokes sidebands, the red and blue arrows that you see there, with suppressed elastic scattering. For optimal cooling, the anti-Stokes sidebands should be on the cavity resonance. And this is what you also see here in the heterodyne measurement of the scattered photons. With this measurement, if you're in the classical regime, the relative height of these Stokes and anti-Stokes sidebands should be given just by the cavity asymmetry. just by the cavity enhancement. However, when you transition into the quantum regime, you suddenly don't have enough levels to go down to, right? So that means that your blue sideband or your anti-Stokes scattering is significantly decreased, and we use that in our favor to do measurements of the phonon occupation. So, for example, this is one heterodyne detection that we have in our setup. As you can see, we see the Stokes sideband here, a pretty small sideband, and you see an anti-Stokes sideband, which is initially enhanced by the cavity envelope. However, there is a small gap to the cavity envelope that shows that we are already in this quantum regime. So this is already an occupation of something like 4 to 5 phonons. And this we can use to measure this occupation. You can also see that we couple a little bit of Z, we couple also some Y modes, so we, in principle, cool all 3 motions at the same time, slightly. So what you can also notice is that the elastic scattering is not really suppressed, it's still there. So we actually have something like 10,000 photons at the moment of this measurement, and this is given just by our precision of the position along the cavity standing wave. So our distance from the intensity minimum is something on the order of 2 to 4 nanometers at any time, any given time. We are not really able to point the particle where it's really sitting at the cavity node. So with this, we have shown that by changing the tuning, we were able to also do ground state cooling of this X motion along the cavity standing wave to something like 0.46 phonons, which means that the particle was around 70% of time in the ground state. And we were limited by the pressure in our system. So our pressure is quite moderate. We are still limited by gas heating by 1 order of magnitude compared to the photon recoil. And our temperatures didn't go as low as, in principle, they would be with a simple optomechanical theory, because our cooling rates are already so strong that we experience some strong coupling effects. For future experiments, we would like to have either 3D ground state cooling or at least close to ground state cooling in the other 2 directions of motion. Note also that there was a significant advance in the feedback cooling of the particle motion. There was cooling to 4 phonons in the group of Lucas Novotny. A recent paper in our group cooled to around 0.5 phonons, and as Massimiliano presented, also in the group of Lucas Novotny was also cooled to the ground state recently. So I'm now going to switch my gears a little bit and show an outlook of this setup. So after Corona setup, let's call it like that. The system of levitated nanoparticles, as I said, is quite a tunable system. So you can invert potentials, you can allow for free fall, but you can also tune all of your experimental parameters, which is something that is not allowed in other optomechanical systems. For example, you can tune the mechanical frequency, you can tune the coupling rate. They all depend on the tweezer electric field or the radius of the nanoparticle, for example. So this would allow us to increase the coupling rate to be in the weak coupling limit, so smaller than the cavity decay rate, use it for detection, or be in the strong coupling limit where we can have coherent energy exchange. And in both regimes, we could do in principle ground state cooling. However, I'm going to talk a little bit more about the ultrastrong coupling, where the coupling rate is comparable to the mechanical frequency of the system. In the ultrastrong coupling between light and matter, we typically use the interaction Hamiltonian so we typically simplify the interaction Hamiltonian by using a rotating wave approximation for small coupling rates in order to approximate something called a beam splitter interaction, which allows us for cavity cooling of nanoparticle motion. In case of high coupling rate, our rotating wave approximation breaks down, so we can't use the simplified Hamiltonian, and we will have a perturbation of the blue detuned interaction with something on the order of g squared over omega. So you can imagine that if g over omega is pretty strong, you can have also significant entanglement interaction in your system, and this would also create some non-trivial ground states of your system. If you look at your systems here, these are all systems that are not working in not really working in optomechanical setups. You can see that the ultrastrong coupling is between the 2 dashed lines, and you can see that most of the progress has been done with polaritons or superconducting qubits in the previous years. In optomechanics, it has been hypothesized that if you are working in the red detuned beam, you are going to reach the ground state cooling. However, there is an overlap region with the entanglement just below the instability region. This would allow for steady state entanglement of your system. Recently, there was also work in John Tufel's group where they managed to reach ultrastrong coupling with their electromechanical systems. Our previous PRL paper was somewhere on the border between strong and ultrastrong coupling, and our recent science paper, where we just increased the tweezer power, went in this direction. Now we are able to trap larger particles in our system, and the green square presents the highest coupling rates that we could achieve at this very moment, which leads us to very unstable regime. Typical signatures of autostrong coupling are strong normal mode splitting and anti-correlation between light and mechanics, for example. For the normal mode splitting, there's two different regimes, strong coupling and ultrastrong coupling. And the difference between them is that in the ultrastrong coupling regime, one of the eigenfrequencies can become imaginary, so you can have a highly unstable system. For our parameters of our particle, we would be able to resolve the normal mode splitting here in this region, and for this region of coupling rates, we would become unstable. We tried already going in this direction, so it really is an unstable system. One really has to be precise with choosing a coupling rate that one wants to work with. We already have some test power spectral densities, and we show that we really have to take the full theory of ultrastrong coupling to explain our spectral densities, because a simple Lorentzian really doesn't work. So this means that there is already some normal splitting, we just can't resolve it because the coupling rate is still smaller than the kappa. On the other side, another signature is that you can have anti-correlations between the light that has been interacting ultra-strong with the particle and a mode that provides a weak measurement. We use dual rail homodyne setup on one side for ultra-strong interaction, and we use a tweezer detection for weak measurement of the particle motion. And typical spectra, as you can see, look like that. We filter our data in the range that is shown with in this range here, and we do correlation measurements between the motion. There are many observed issues that we have seen so far. They mostly really resolve into how well do we know the tuning in our system. And I will just show an example. So our theory for the parameters of our system shows that the correlation depending on the optical phase and electronic phase should look something like that. If you draw a diagonal here, and this diagonal cuts the measurement to the negative values, then you could claim that you observe some entanglement in your system. Our measurements show that we don't have any overlap with the negative correlations at the moment, so we don't observe any anti-correlations. This could, however, be also due to really not knowing the tuning precisely in our system. So as I said, so correlations are highly sensitive on variations in the tuning. Also, we know that the relative signal delay between tweezer and cavity detections is also sensitive on variations in the tuning, and we are working toward setting up yet another cavity mode for detecting of the nanoparticle motion. So with that, I just want to briefly mention, so we have implemented this coherent scattering method from atomic physics, and now there is a whole new generation. Yeah, I was muted for a moment. Yeah, so there is a whole new generation of experiments in cavity levitated optomechanics based on this method. I have shown that it's highly tunable setup. We can scan quite a huge parameter range, go over many different interaction schemes, so from weak to strong to ultra strong and to deep strong coupling rates. As an outlook, we are going toward the stationary entanglement and simultaneous ground state cooling with this setup. With that, I would just like to thank the team, and so also collaborators, Marko Toros, Tanja Montiro, and Vlada Vuletic. And of course, this is pre-corona meeting, so we like to have these ventures into the wild, and I'm kindly asking for your questions.
Okay. Yeah, Uros, thank you very much for very interesting talk. I didn't stop you because I was monitoring chat for questions, and yes, that's, yeah. Well, now there appears a few questions, but we'll just keep to the first one because we don't have really the time, and it's from Raquel Flores. Thank you for the interesting talk. Experimentally, how do you precisely position the mirrors of the optical cavity? And what is the tolerance of that the system can have in terms of misalignment of the mirror's position?
Yeah, so actually what we have, I'm gonna try to quickly go back if I can somehow. What we have is actually our optical tweezer or our microscope objective is sitting on a translation stage. So the mirrors are actually fixed. The cavity mirrors actually go into this holder, as you can see, and they're clamped in this holder. And that's basically it. The microscope objective on the other side is sitting on a translation stage, so we can move our particle in and out of the optical cavity. The cavity itself is a confocal, roughly confocal cavity, which is the most stable configuration that one can in principle have. Which means that we don't really have to take care of any stability or whatsoever.
Okay, then maybe just one more question that is from Lucas Novosny. Very nice and clear talk. You mentioned that your experiments are just in the strong coupling regime, which means that the spectral peaks are mixtures of mechanical and optical modes. Does this have an influence on the inferred mechanical occupation number?
Actually, so this is a good question. This is what we asked actually when we were evaluating our data. So heterodyne measurement is giving you an average of the variance along X and P, and so you actually get an average of the whole state. Let's call it like that. It's an average of phase and amplitude measurements. If you're just integrating your area, you don't have to take care of how your peaks actually look like if they are split or not. The integrated area is the occupation itself. The line that so if I just the line that was there, the green line that shows how much errors we actually have on our measurements. So basically, this thing here is the whole theory that already includes the strong coupling in our system. So actually, it already includes the theory that says it's gonna be a little bit of a squeeze state or thermally squeeze state. I'm not sure if the variance actually goes below the shot noise or not.
Okay, Urs, I thank you for the presentation and answering to the questions. There is one more question in the chat room, but we have to move on. And I invite Ivan Toftul from ISMA University, St. Petersburg, to present the talk, Stable Self-Trapping of Nanoparticles via waveguide modes of a nanofiber.
Hello, thank you everyone for the introduction. Let me share my desktop. So this talk is actually devoted to only the classical electrodynamics, so nothing quantum here. And this is purely theoretical work. And as the title suggests, so this is about the self-trapping of nanoparticles with the help of guiding modes of the nanofibers. In other words, it's about optical binding next to the waveguide modes. So the brief outline of my talk will be always on the top of the slides. So I'll start from the introduction. So I'll start from the optical forces in general. So since the works of Arthur Ashkin in the 70s, since that time, it was a great breakthrough in optical tweezing, and people achieved a very precise control of matter using by light. So, and the best thing about such approach is that it doesn't distract objects which you trap. For example, there was an experiment in 2008 where where they managed to trap the DNA molecule and the molecule of RNA polymerase. So this one, they glue it on the silicon nanoparticle. They put both sides of the DNA into the different tweezers, and they managed to measure force which this DNA polymerase experience when it reads the DNA particle. Also, people achieve something like a 3D holograms using fast-moving atoms or small particles. So they managed to create 3D atomic assembles. Besides this, there are also a huge area of trapping of not single particles, but the collision of particles, the clusters of them. And the interesting feature here is when you trap two or more particles which are very close to each other, they start to interact with each other. And this gain many interesting features. For example, there are various stable configurations are possible. So these are self-organizing systems. So here on the slides, you can see examples in the free space or next to the substrate. Also, such experiments were done next to the waveguides, for example, in these works, where some periodic arrays of 1D arrays were realized. And here in our work, so we present the next configuration where we used a single nanofiber and we place several nanoparticles, an array of nanoparticles, and we put a transverse pump next to it. And we will show that actually the interaction energy will grow linearly as the number of particles increase. So this is the optical binding effect, which is the stiffness of the trap is the higher when we increase the number of particles. So I will start in order to understand how does it work and how we achieve this theoretically. I'll give some brief theory on the optical forces in general. So suppose we have a small particle, and if the particle is sub-wavelength, it supports only the dipole moment, which can be induced by the incident field, which has some electric field E. And this dipole moment is proportional to the electric field with a coefficient of proportionality alpha, which is the polarizability. And if you write the interaction energy, which is P dot E, so the dot product of the dipole moment and electric field, and then we'll take the gradient of this energy and we substitute everything to this formula, we'll actually get the very simple result, which show that the force is proportional to the gradient of the field intensity. And this suggests that our dipole goes towards the high intensity gradients. So, but this is a very simplified picture. So this is the electrostatic picture. Of course, if we go, for example, the Gaussian focused beam, which is the Gaussian. So the more general answer to this question, so what's the force on the particle and the light? So will be something like this. So there are actually two parts of the force, which we can decompose by decomposing into something which is proportional to the real part of the polarizability, and the second part which is proportional to the imaginary part. So the first part is actually is the same as in the electrostatic approximation, which is the gradient force. So this force actually puts our particle to the high intensity region, but the second part actually is proportional to the Poynting vector of the field. So it's nothing but the light pressure. So now we know how the light works, so how the optical force works. And what happens if we put two particles next to each other? So suppose we have two particles and the incident field is propagates perpendicular to our screens. So each particle has induced dipole moments and they start to radiate because those dipole moments oscillate. And since they radiate in phase, so they're coherent, so we have some interference pattern in the region where they scatter. So, and since there are some local gradients, we expect that there are some optical forces which is transverse to the direction which connects two particles. So if we calculate the force in the free space from the plane wave on two particles, we'll actually gain something like this. So here's the x component of the force from first particle, which acts on the second particle. And if you look at this force closely, we'll see that actually it changes its sign. So it's sometimes it's positive, sometimes it's negative. So it's the dependence with the distance between those particles. And if we put second particle here, so the force is positive and it pushes particle to the right. But once it crosses this region, for example, it's happens to be here, the force starts to be negative. So it's pushing the particle back. So this is a stable equilibrium position. But unfortunately, in free space, this interaction actually decays as 1 over r squared, because the radiation fields actually decays very fast in the free space. But we asked the question, can we make this interaction long range? And yes, we can. We need to use something which has a very long range propagation modes. So, for example, the waveguides. So if we put the waveguide next to those two particles, we can expect the long range interaction. So we managed to do this, and let us consider only two particles first with the waveguide next to it, and we calculate the longitudinal force. So what we can expect, so we have two particles and they interact through the vacuum as in free space as before, but now they have the different channel of interaction, which is through the wave-guided mode. And for simplicity, let us suppose that this is a single mode fiber and this is only one single channel of interaction. And this waveguide mode can propagate for a very, very long distance, since we can transmit signals through the optical fibers for kilometers and more without significant losses. And if we calculate the optical force, it appeared to be periodical and non-decaying for a very long distance. So now if we decompose that force into the vacuum contribution and waveguide contribution, we'll see that the vacuum contribution actually decays as was shown before for this free space, but the wave-guided mode actually tends to be almost constant. The amplitude of the wave-guided mode tends to some constant and doesn't depend on the distance. So if we zoom in some region, we actually have the same picture as before. Some points are stable, some points are unstable. And next, we got an idea. So this is the interaction picture of two particles. So, and we have many equilibrially stable positions. What if we put the third particle in the next stable position? Okay, let's do this. So this is the mechanical analog of our system. So this is our two dipoles which interact with each other. So this is something like a spring connection. So those particles are connected with a spring. So next we add the third particle, and it actually interacts with the first and the second particle equally because the interaction does not decay. So this particle so the third particle interacts with the second particle the same as with the first particle. Next, we add one more particle, and actually the number of links grows because due to the long-range interaction nature of the system. And if you look at the depths of the potential energy, we will see that actually it grows linearly. So once we have two particles, then we have three, the interaction energy grows, then four, it grows even more. And here in this example, they all equidistantly placed. But there is one very tricky question. So what is the equilibrium distance? So at what distance we should place those particles? And this was not a very trivial task because it's not a half wave, the number of half wave wavelength or something like this. So the answer appeared to be quite interesting. So if we look at the plot on the bottom, and so here we have the number of particles as the x-axis, and on the y-axis we have the distance between particles recalculated as in terms of the phases between those. So this 2 pi distance between particles divided by the wavelength. And for the two particles, it's we have the rigorous answer. So it's 3 pi over 2. For the infinitely many particles, we also have a rigorous answer. So it's a 2 pi distance. And for the intermediate, we have something like this blue line here. So for different number of particles, we have different equilibrium distance between particles. So this is our distance. But if we look at the plot on the top of the screen, and so if we calculate the trapping energy normalized to the energy to the interaction energy between the two particles, we will see that it will actually grow exactly linear with the number of particles. And we also achieved the analytical formula for this. Well, okay, it grows linearly, but is it stable enough or not? To answer this question, we compared this interaction energy with the KT of the environment. And for the room temperature and for the reasonable powers of the lasers, we achieved numbers something like 100 KT, which should be, it means that this should be very stable. So now we discussed the longitudinal trapping next to the nanofiber. So this is done, but we need to position those particles in 3 dimensions, and we don't want to forget about the radial trapping and the transverse azimuthal trapping. Well, so what about those? So it is also possible by the 2 beam configuration. So on the left, here on the center, this is a cross section of the fiber, and if we put 2 counter-propagating beams, which are coherent, so we have some interference pattern, and due to the lensing effect of the fiber, due to the rescattered field, we can achieve some hot spots near the fiber, which actually creates both radial and azimuthal potential traps for the particles. And for example, if we draw this line here, so this is axis S, which is located here, and we calculate the trapping potential, actually it's pretty strong with the reasonable powers of the lasers. So it should be enough to trap to hold the particles pretty stably. So here comes to the conclusion. So we showed that the guided modes allow to achieve long-range interaction. So we can beat the short range nature of the direction by introducing some, placing those particles next to the waveguides. We could achieve the transverse and radial positioning by the scattered field of the fiber, and so it's actually the jet effect or fiber lensing effect. And the third thing which we think which is very interesting. So this is an example of very unique system where the more particle we put there, the stiffer and the more robust it becomes. So this is pretty unusual for our everyday experience, and actually we're limited here only by the waist of the laser, which pumps our system, but still within the waist it grows linearly. So I also really want to acknowledge my colleagues, Misha Petrov and Daniil Karnaval, who contributed to this work. And thank you very much for your attention. And I guess I'm ready to questions.
Thank you, Ivan, for interesting presentation. And I have just open for the question. So I can see there is a question from Louis Rooks. Thank you very much for the talk. As the coherent forces between particles result in the linear increase of trap depth with particle number, I would expect that the incoherent scattering effect should also increase heating. Does the time for which the particles are bound increase regardless?
Thank you for the question, Luis. So as for the losses, okay, this is a big question about the heating. So as for heating, people while doing the experiments, they actually does not do it in vacuum. They actually put everything in water to have better conduction of the heat. I'm actually not sure what exactly you mean by the increased heating due to the incoherent scattering. I guess it doesn't really depend on the coherent or incoherent, because heating will be proportional just to the imaginary part of the epsilon of the particle.
Okay. Well, since it's not me who asked the question, so maybe we should move to the next question from Anil Kumar. The question is, more the particles, stronger the pump is required. Is it so?
Okay, so of course, system cannot gain the energy from nowhere. So this result. So all the theoretical calculations were done by putting the plane wave as a transverse pump, and the power of plane wave, because it has it propagates infinitely everywhere, so it's infinite. But once we have, for example, the laser with a very huge waist, and we fix the power in it, and if we put the particles within the waist, it will not. So it will still grow linearly within the waist, and with the fixed laser power of the incident field.
Well, for me, it sounds reasonable. And, there is also the question from Jansin Chen. Is there any direct application of the considered system?
Okay, thank you for this question. We thought about this. Probably, I don't know any like systems to sell next year, something like this. But one of the possible applications could be the following. So we put some periodic structure next to the nanofiber. So this is periodic perturbation next to the guided, next to the waveguide. And for example, this could be a tunable Bragg mirror. So the equilibrium distance between particles depends on the transverse pump of the wavelengths of the transverse pump. So if we tune the wavelengths of the transverse pump, we can tune the distance between the particles in this array. So we can tune the band gap of the Bragg mirror by tuning the wavelengths of the transverse pump and changing the transmission through the system. So this could be one of the examples.
Okay. Then, yeah, the last question that is from Ibrahim Issa. Thank you for your presentation. There are many waveguide modes. So, which waveguide mode should one consider to enhance the interaction? So, yeah, this is another big part of the investigation. So, we considered only the fundamental mode, which is HE11. And no, I think I have only for the single mode. So we considered also the higher modes, the higher mode regime of the nanofiber. So if we increase the radius of the fiber, there are many possible propagating modes, but actually the system goes pretty not so predictable when we have multiple modes, because each propagating mode has different propagating constant. And if we have various channels and each interaction channel has different propagating constant, so we have some beating effects within the interaction. So we don't have very clear picture which doesn't grow exactly linear. So we did some comments in this paper. So there is a section about this, but the general answer is the system works very predictable for the fundamental mode. This is true. Okay. The time is also up. So thank you, Ivan, and thank you all presenters of this session. With this, we close the session and we convene at 5:15, and we have a break until then. Bye. Thank you.
Thanks very much, Louis. It's a pleasure to be able to speak at this wonderful conference that I really like. I have to admit that usually I complain about the difficulty of getting to Banaske, but this year I wish I could take that difficult route and actually be there in person. But again, I'm very grateful that I'm included in the program nevertheless. So as the title says, I'm trying to tell you as much as possible, and I've come up with this title to try to include a couple of different projects. I hope it makes sense at the end to you. So let me start by thanking the people who are working in the area of quantum optics in our group right now. So the people in the first row are the people with permanent positions in Erlangen, and the second row are postdocs, and the bottom row are PhD students. And so we are looking for some postdocs. So if you like what we do, please feel free to contact me at some point. So let me jump right in and with a kind of very quick introduction. When we talk about the coupling of a photon and a two-level system as the most fundamental, let's say, building block of light-matter interaction, quite often we write the Hamiltonian in the simple form of E dot D, And then, you know, you worry about a matrix element like this, and then you do all your calculations as you might be used to, for example, in cavity QED. There is an alternative way of looking at things, which is a little more phenomenological. That's quite useful. I particularly like to think in this term. And that's just looking at cross section. So let's say that you have your atom and you illuminate that. Now this atom could absorb light. If it's a two-level system and there's no absorption, but it just scatters. Either way, in transmission, if you were to look at it, then you would see that you get a certain signal. For example, on resonance, there's some light missing. And you could associate an interaction power that would be proportional to some kind of a cross section that you associate with this interaction, and then the area over which your light was confined, and P naught would be the incident power. The sigma turns out to have a very simple form. Essentially, just depends on the wavelength of the transition in this two-level atom. So either way, you can describe things also quite rigorously. And I'll go back and forth, or let's say I use this formalism particularly as an intuitive way of walking you through what we do. Now, one thing that you have to keep in mind, though, is that when you couple your atom to a medium, especially if your quantum system is in the solid state at room temperature or at a finite temperature, then there's coupling to the matrix. And there is thermal agitation, and there are lots of modes that are involved. So what you have to worry about is a factor in front that usually results in the reduction of this cross-section that we just talked about. So the cross-section in its perfect form in vacuum would be quite large. It's of the order of lambda squared divided by 2. But this gets reduced by this factor, and this factor is now the ratio of gamma 0, which is the spontaneous emission rate. So just the radiative decay of the excited state over the overall line width that you would have. And that overall line width could have different causes. Again, radiative decay is one possibility, non-radiative decay is another possibility. And then, of course, you could also have dephasing. So this dephasing could come from a kind of a phonon bath, as I was mentioning before. And the point is that at room temperature, this is of the order of 100,000 times stronger than your spontaneous emission decay rate. So this sigma that we talk about becomes something of the order of 100,000 times smaller as you take an atom from vacuum and put it in some kind of a solid at room temperature. And you can think of this now as basically decoherence because you have lots of modes that you've coupled to. When we go to very low temperatures in a particular system, and you know lots of systems, and many of them are also discussed at this conference, you can find, you can reduce these phonon couplings and get to narrow lines nevertheless. That is, that ratio of gamma 0 divided by gamma, you can try to make as small as possible. Now, the system that we like to work with is typically shown here. So you would have some molecule that looks like this, for example, in this case, dibenzotyrrolene, and then that molecule is embedded in a crystal, for example, anthracene. What you see here is a contour of an anthracene crystal, and inside, as the frequency was scanned, you see that individual molecules are lighting up. These molecules are sitting at different locations, but they also have different frequencies because they're in a matrix, and therefore there is an inhomogeneous distribution of frequencies. And that's exactly what lets us address individual molecules. So you tune your frequency and therefore be able to talk to one molecule at a time. Now, these molecules have a typical kind of molecular energy scheme where you have a ground state, electronic ground state, and an electronic excited state. But you also have to worry about vibrational degrees of freedom for both the ground state and the excited state. Now, if you go up, this would be the requirement of our two-level system. But once you're in the excited state, you have the possibility now to decay via all these vibrational states. And these are typical kind of Stokes-shifted, red-shifted fluorescence channels that you know from your dye molecules or fluorescence microscopy. In this particular system that we worry about, these the molecules like DBT, they have a very favorable branching ratio that is something of the order of 30% to 50% of the energy decays via this main transition, and the rest goes via these vibrational states. Now, these vibrational states in a solid are coupled to the matrix, and therefore they decay quite rapidly. And this basically creates a certain decoherence channel also within the molecule. And we can attribute that by some factor, kind of a fudge factor, alpha, that is of the order of 1, but let's say, or 0.5 or something like that, as shown here. All right, so this is to say that that wonderful cross-section that I told you about is good for a two-level system, but in a real system, even if you have something like a quantum dot, you typically don't have a two-level system, so you have a more complex kind of decay channel. And the way to fight that or go back to that pure two-level system would be to enhance this transition, make this transition very fast. So that the ratio of the rates of coming down via this channel versus other channels becomes a lot more favorable. And one obvious way of doing that is to put the molecule in a cavity and tune the cavity to this resonance. And by doing that, you enhance this transition. In the language that I've been using with cross-sections, this can be understood quite nicely, where you put your photon inside, but the photon now doesn't have one passage, but is circulated back and forth. And the number of times that it goes back and forth is essentially given by the finesse of the cavity. So you win by proportional to the finesse, but you typically lose in the cavity compared to that let's say, a strongly focused beam that I will tell you about later, because the waste of the beam in the cavity is usually finite, let's say omega 0. So the figure of merit that you have for your enhancement is F divided by the mode area. And ideally, you want to make your finesse large and you make your mode volume as small as possible. If you rewrite this, you can show that that's the same thing as writing Q over V. And again, you would want to make your Q large and your V small to get a large Purcell factor. And that would mean that you enhance this. Now, these transitions are not resonant with your cavity, therefore they are not going to get enhanced. If you rewrite that again, you can also show that this is essentially the same thing as cooperativity. Okay, so let me see now. The way we go about this in our lab is we try to make very small mode volumes so that we don't have to have Qs that are too large. And that has several different reasons. But to make very small mode volumes, we fabricate mirrors that have very small radius of curvature. And the way we make our cavities is actually a configuration that consists of a flat mirror. So this is a distributed Bragg reflector, if you want. And then on the other side, we take something like the end of an optical fiber or the end of an AFM tip, and we use focused ion beam milling to make these mirrors with very small radius of curvature of the order of a few microns. And by doing that, we can make a cavity now, an open Faber-Perot cavity that is very small. And of course, this upper mirror that we have carved is sent to a company to get multi-layers, and so you get also a highly reflecting mirror on top, and overall you have this microcavity. Then on the flat side, we put a thin crystal of anthracene. This is a picture of anthracene crystals. You take one of these flakes that is very thin, only a few hundred nanometers. In that you have doped DBT, like the image that I showed you earlier. And now you establish your cavity. And of course, in the cryostat, we have to be able to adjust all of these independently to be able to put the molecule of interest in the antinode of the cavity mode, and also in the axial direction. You want to tune the cavity to the resonance of the molecule that you want. Then you use a lens to couple into this cavity, and you're good to go. So in a nutshell, I show you some results. This would be the transmission of the cavity, of the empty cavity, when it's not resonant with a molecule. So in reflection, this is how it looks, and transmission, this is the signal that you would get. And now if you tune the resonance of the cavity to one of the molecules in the sample, then you would see that you completely change the spectrum. And for example, in transmission, you see that your transmission breaks down to almost zero. And at that point, the light is reflected. So again, in a simple word, what a single molecule has done is has completely changed the index of refraction of the cavity to make it no longer resonant where it used to be resonant. You can study this. We can look at the same molecule with and without the cavity, and you see that without the cavity, you have something like a line width of about 40 megahertz. And with the cavity, this would be of the order of 600 and some megahertz. And when you do your analysis, you can show that we had, in this case, a Porcelain Factor of about 40. So by enhancing that main transition 40 times, we're getting a branching ratio now that is well beyond 90%, whereas we started with something like 30%. So you end up turning something that is quite complex with lots of energy levels and transition possibilities. We turn that into essentially something like a coherent two-level system. And again, there is no difference in the physics that I'm telling you, whether you use a molecule or a quantum dot or a color center or 2D materials. The physics is always the same. Now, what I showed you was published data. What we've done more recently is to push from a technical point of view to get the cavity to be to perform better. And by doing that, we have managed to enter the strong coupling regime. In the previous experiment, we were almost at the end of the weak coupling regime, beginning of the strong coupling. But now we're in the strong coupling, not very deep into it, but we are in it. And you see here that we get this splitting that looks similar to before, but it is now actually more pronouncedly having a lower polariton and an upper polariton. But more importantly, if you examine that in the time frame, then you see that you clearly see not just the decay, but you also see the indication of the Rabi oscillation that you expect in strong coupling. So these results, I'm not going to go into details. This is presented by Andre Scherer in the poster session on Thursday. But in a nutshell, when you're in this strong coupling regime, you can get the molecule to be saturated with 1 photon per cavity lifetime. So the coupling is strong enough that an extremely weak excitation already saturates the molecule. So this is a typical kind of saturation curve that we would obtain. But more excitingly, we've shown that you can do a kind of a pump probe or a gating type of experiment where we have a pump that we call pump, but it's actually extremely weak. And then we have a probe that is even weaker. And by turning the pump on and off, we completely control the passage of the probe beam through the cavity. So this is the main cavity. The pump and the probe now are quite close in frequency with respect to each other, so about 300 megahertz. The probe is sitting resonant with the whole system, and the pump is a little detuned. And by turning this pump on and off, we control the passage of the probe beam. So you see that normally the probe is not going through because it corresponds to this dip. And as we turn the pump on to have 1 photon per cavity lifetime, then the probe is now almost completely going through. So you begin to develop a kind of a switching or gating at the level of single photons. So if you think now about this cavity QED type of situation, I told you about weak coupling, strong coupling. You heard before that you can also go to ultra-strong coupling regime. But the essence of all these things is that the light in the cavity undergoes multiple reflections. There is an interference that happens, and you have a resonance. So that's one of the important features of a cavity, that you have a well-defined resonance, and with that you're modifying the density of states. That also corresponds to the fact that you are storing light for a certain time, so there's a Q associated with it. You can also define a finesse that then also has to do with the mode volume. So these are all the different kind of buzzwords or parameters that you worry about when you do cavity QED. I think this community knows that you can basically try to do cavity QED without a cavity, but with something that is more like a nano antenna. When you have something like a plasmonic particle, again, you have a resonance, and this resonance has a certain line width or a certain lifetime. These lifetimes are extremely short. They're now typically more in the 10 femtosecond regime instead of a few nanoseconds or microseconds. But that also means that you have a broadband system that has its own advantages. The other advantage of an antenna system is that the whole thing is quite compact and it's sub-wavelength, whereas a cavity always is, at the end of the day, even if you make the smallest cavity, it has a fairly large footprint compared to wavelength. But then, of course, you have to do near-field coupling to an antenna. And the not so nice thing about antennas is that they always are accompanied with some finite losses. Okay. Now, antennas have been studied quite heavily in the past little less than 20 years or so, but most of the time people have been interested in enhancing fluorescence or spontaneous emission rate, and most of these things have been happening at room temperature. So this is a couple of examples of our own work, where in the very early days we showed that we could change the lifetime by a factor of 20. More recently showed a nano-cone antenna that we could enhance by a factor of 110 or so. But again, in these experiments, one detected fluorescence. That means that the actual experiment that was happening was an incoherent communication with the antenna. In the past few years, several groups have shown that they can also go towards something like strong coupling using antenna systems and plasmonic systems, and doing coherent coupling, for example, here in the group of Chen Xiaodong, where you see that you begin to go towards a cryogenic regime, and you get things like Fano resonances. We have also done some new experiments that I'm not going to tell you much about, just flash this one slide, but we're preparing a manuscript where we show that we can indeed get also a strong coupling type of situation by putting realizing an antenna that looks like this, where we, in a controlled way, we move a gold nanoparticle close to a quantum dot on a gold layer. So this is now the antenna. So this works at room temperature. That's the advantage of it. And if you want, it's equivalent to the cavity thing that I showed you. But what I really want to talk to you about today is an experiment that we published last year, where we tried to look at the coherent interaction of an incoming beam and the compound of a molecule and an antenna. So again, think of the antenna as something like a cavity. So the molecule coupled to the antenna becomes quite similar to a molecule in the cavity. And now if we look at the passage of light through the whole thing, we want to see what kind of signature we get. Again, the molecule is going to emit like a dipole with a dipolar pattern, but my nanoparticle is also going to emit essentially like a dipolar radiator. And these two in the near field actually couple to each other and affect each other. And so on the detector, I'm seeing the effect of that interaction, but also I'm seeing the interference of three fields now: the field that is incoming, the field that is scattered by the particle, and the field that is scattered by the molecule. We had predicted this theoretically a few years ago. In a nutshell, we showed that if you were to, for example, look at the profile of a focused beam, and if you put an antenna in it, then of course this antenna is going to scatter the light, and therefore the profile of the beam is completely changed. But if you were to add a single quantum emitter to that antenna, you would be able to recover the profile of the beam. That is, you're essentially cloaking the antenna with by one single molecule that you couple to it. So we wanted to realize something like that in the lab. And so again, this is the situation that we want to realize. We want to couple a molecule close to an antenna and now see how much that affects the transmission of a beam through the nanoparticle, which again, you can think of as the cavity. The way we do the experiment is we nanofabricate gold particles, or discs in this case. These are actually gold particles sitting on a little glass pedestals. Then we distribute our molecules in a matrix, in the matrix that we have. For example, in this case, it wasn't anthracene, but imagine that it's something like anthracene. These molecules are going to sit randomly, but they have a fairly high density, so close to every nanoparticle there are many molecules. But we can distinguish these molecules now in frequency space because we're working at low temperature and these molecular lines don't overlap with each other. So we're going to we're going to focus onto one of these nanoparticles. And of course, the nanoparticle is only a few 100, 150 nanometers large. Our focus is more of the order of 250, 300 nanometers. And there would be many molecules that would be excited in that way. And now what we want to do is we want to shine this with the beam that I was telling you about. Now, there's going to be some fluorescence from the molecule that we can collect, but then we're also going to look in transmission and see what kind of signal we get. This is the core of the optical setup in the cryostat. The sample would be sitting here, and then you would have lenses that allow you to focus onto the sample and collect the light in transmission. Sorry, I'm coming from the other side. So an experiment like that you can actually do on a naked molecule, and because of that large cross-section, this naked molecule ends up having a large extinction dip. That is, if you just look at the transmitted light, you see that a single molecule puts a large dip, and that's because the cross-section of the molecule is very large, as we had said before. And now what we want to do is we want to add that nanoparticle to it. And this is the signal that we record from many molecules within one focus. And if we show the whole thing, then we recognize that there's one line that is particularly strong. It turns out that, and you can do lots of checks, we report about that in the paper, but I'm not going to go through the details of that here. But you can show that this molecule now is actually coupled to the gold particle. And we can show that this molecule, for example, although it's stronger than others, is not coupled to the gold particle. What you see now here is the shadow of the gold particle as we look at it in transmission. So you see that as the beam is scanned over the gold nanoparticle, you see a dark spot because the particle is scattering the light out of the beam. And on top of that, I'm showing you the localization result of the particle. That's the yellow dot. So we can localize the particle and say that its center is here. But then we also can localize that coupled molecule and show that its center is here, and localize the uncoupled molecule and show that its center is here. So either way, we see that those two molecules are quite close. Their polarizations we can examine. We know about their polarizations, and now we can do extensive studies on each one of these molecules because we can address each one separately because they're sitting at different frequencies, as you see. So this is a second-order autocorrelation function that you record from, in this case, the uncoupled molecule, and we get the lifetime of the molecules, of the excited state from it. And that amounts to something of the order of 8 nanoseconds. And this is the equivalent G2 function that we record from the coupled molecule. And you already see that this coupled molecule has a considerably shorter lifetime, which is as expected because the molecule is coupled to the gold nanoparticle. We can also do extensive saturation studies on each of these molecules. And also here you see that the molecule that is coupled, it saturates later, and actually it is giving you a lot of light. So we're getting a stream of single photons with something in this case of 8 million counts per second. In fact, we had other molecules that we went all the way to something of the order of 50 million counts per second from a single molecule in this arrangement. Okay, so now we want to see whether there is this induced transparency or partial cloaking. Again, the arrangement is as shown here. I told you that if I don't do anything, if I don't have the molecule, then I see a shadow from the gold nanoparticle. If you want, that's the transmission of the through the cavity. This is the shadow that I was telling you about. And on top of that shadow, now we want to see what happens if we have a molecule. Or you can also ask the other question. You say, if I just look at the molecule by itself, what happens? Well, if the molecule is not coupled to the gold particle, it has this type of a dip. So you see that in this case is something of the order of 4% dip. But for the molecule that is coupled, we see that we actually get a peak. And this peak is now, it means that we get more light with the molecule than without the molecule. Remember that without the molecule, we have a shadow. So the shadow is becoming about 10% weaker because there is a molecule in front of it. So this is essentially what the theory predicted. And the nice thing is that now we're not doing fluorescence measurement, but we're doing coherent measurements. And if I put that in the context of the experiments that I showed you before, the experiments on the right are also exploring now more of a coherent type of interaction or strong coupling at room temperature. But your quantum dot or molecule at room temperature is really not a very coherent system. The line widths are extremely broad. As I told you, they're about 100,000 times decohered. And what we have done is we've gone all the way to low temperatures where the intrinsic coherence of the system is as good as its Fourier limit. Again, we're getting a narrowband induced transparency, narrowest than has been seen before, and we're right now in this experiment, we're actually far away from strong coupling, but we're very much in the regime of coherent coupling. So that's the story that I actually wanted to tell you about, but I want to flash a couple of different things that I didn't talk about, but again, as mentioned in the poster session, we had a very nice collaboration with a group of Paul Zeidler at IBM Zurich, where we looked at and developed a gallium phosphide waveguide platform. You might know that we have an experiment on where we couple molecules to on-chip resonators and waveguides, and in this case, we were exploring gallium phosphide as a high index type of medium, and it turned out that we actually were quite sensitive to charge fluctuations, which are very small in gallium phosphide, but if you visit Dominic and Dominic's poster, then he will tell you all about the details of how we use single molecules to sense the small electric field of fluctuating charges in gallium phosphide. And finally, I also want to advertise the poster by Buvak, who has done a theory work and is going to tell you about the efforts together with Diego, as he was still in Erlangen, where we tried to find ways to exploit a molecule more as an optomechanical system. And he will tell you about how to couple a molecule to the acoustic modes of its environment, and by doing that, try get to long-lived states in a molecule that you could possibly use as quantum memory. With that, I thank you, and I'll be very happy to answer any questions.
Well, thank you very much, Pahit, for this very nice talk. Let's see. Yeah, there's one. We have time for one question, and there's one by Christophe Galland that says, do these molecules ever bleach or get photo damage? If so, at which typical power? What is the impact of the plasmonic antenna on that? Also, do you see local heating of the plasmonic antenna and its impact on molecular language?
Yeah, so we can do fairly high power. You can go to a saturation parameter of 100 and you don't bleach these molecules. So you don't have to worry about bleaching of the molecules in this system. And of course, if you were to dump that much power in a gold nanoparticle, then you would heat it. And you could eventually see the effect of that on the line width. But when you're working at the typical powers that are of the order of saturation parameter 1 or 5 or 10 or something, the heating effect is negligible. So we don't really see any limitation due to heating of the plasmonic particle.
Okay, thanks a lot. I think we have to move on. So if there are more questions, perhaps Pahit can answer them by mail. So we move to the next speaker. That is Javier Aizpurua. Javier, are you there? Yeah. So, and he's going to speak about extreme molecular spectroscopy and microscopy in picocavities.
Yes, thank you. I'm trying to start my camera too. I don't know if you can see me or not. I'm afraid I cannot start. Can you see my screen?
We see the screen. We don't see you, but we do see the screen.
Yeah. Yeah, I don't see this screen. I don't. The screen just suddenly changed, but well, I will continue without my screen. I think it's better to see the speaker, but I'm trying to start it, and I cannot. So if David can turn it on, that's okay. Otherwise, I start. Okay, Luis?
Okay.
Good. So thank you very much. I want to thank you, Luis, and Francisco, Sergey, and Lucas for having me here. And it's really a pleasure to address this community. I'm going to talk today about something which is a little bit of a continuation of what Bahit has been talking about, connecting nanoscale cavities and emitters. And in order to do so, I want to first acknowledge my group. It's a bunch of people, young and very, very capable, and I'm very thankful to them. And much of what I will show, it's connected with what they are doing, right? But on top of the ongoing students, I have also three special collaborators: Nikolai Schmidt, Yuan Zhang, and Thomas Newman, who are in Macquarie, in Shenzhou, and in Strasbourg now, and I will show quite a lot of things that I have been developing. It's hard not to consider them part of the group because they have just graduated very recently, but now they run their own careers, and it's not part of the group anymore. So I put them now as collaborators, not as group members anymore. On top of that, I want to acknowledge Andrei Borisov, as usual, a friend and a good collaborator of the group, and other friends and collaborators: Francisco Garcia Vidal in Madrid, Daniel Sanchez Portal Angueza Guezque here in San Sebastian, Alejandro González Tudela in Madrid, and three experimental groups that I will show a few results on: Jeremy Baumber in Cambridge, Guillaume Schul in Strasbourg, and Sen Chaodong in Hefei. Okay, basically what I'm going to talk about is excitation of molecules in a quantum nanophotonics context. And these are the kind of spectroscopies we can do on vibrations, check excitones and vibrations directly through infrared absorption in vibrations, or through electronic transitions via fluorescence or off-resonance Raman. And this is what we want to improve by putting our molecules in the cavity, our emitters in the cavity, right? That's the kind of cavities we're going to use. It's nano antennas. Plasmonic nanoantennas, metal nanoantennas that trap and localize field, and they are very effective for this kind of spectroscopies. And I remember like 2 years ago, right, in Telluride with Bahit Sandogar discussing about the fact that I was quite often talking about nano cavities, and because of cavity QED that we use in this context, when we actually didn't have a cavity, right, and that we were abusing a little bit the word nano cavity in this kind of open particle, right? So sometimes we would prefer to talk about the nano resonator, was Bahit says as a nano antenna. Nevertheless, if this is a problem, we just need to add a second particle here, build a proper physical plasmonic nano cavity, and then we can still talk even physically about nano cavity. You wish, or you choose your best term: nano cavity, nano resonator, nano antenna, enhanced spectroscopy. Okay. We put our molecules, our emitters, our vibrators close to the near field of these antennas, which have very low effective mode volumes, and we will increase the rate of light matter interaction. As a theoretician and as a group of theoreticians, we need to approach the interaction of these light emitters and nano cavities with different theoretical tools, right? And I'm going to just outline the three tools we typically use and give some examples of that before I enter into extreme picocavities, right? The first approach everybody's familiar with is this electrodynamics. We have the emitter in the middle of some kind of material dielectric responsive resonator. We solve Maxwell equations, and we include the emitter as a point dipole, as a current, maybe with byronic structure, depending on the sophistication. And with that, we can address electromagnetic coupling, weak and strong, light emission, surface enhanced spectroscopies, all sorts of nanophotonics and even picophotonics, as I will show you in a second. Right? But there's another aspect. When we go beyond electrodynamics, we pay more attention to the electrons building the metals and interacting with the molecular levels and quantum dot levels, the HOMO-LUMOS, charge transfers, nanoscale transport, optoelectronics, and this we do with solutions of the dynamics of the electrons themselves. It's still classical fields, but we solve time-dependent Schrödinger equations, sometimes with this time-dependent density functional theory to describe the electrons, and this provides a very powerful tool to address subnanometric interaction and charge transfer and transport processes, which are missed by classical electrodynamics, right? There's a third approach, which has to do with this cavity QED. Now here we will use nanoantenna QED, Bahit, okay? So it's fine. And we will quantize here the local fields of our resonators, of our nanoresonators, nanocavities, nanoantennas, and we will solve the Schrödinger equation by solving the master equation with Lindblad operators and operators that take account of the large losses of our plasmonic resonators. With this, we address a different type of problems, and I will show a few of them. And in some of the posters in this conference, some of these are addressed as well. Non-linearities in light matter interaction, statistics of the light emission, non-classical light generation, etc. Right? So let me show you very quickly one example of the three. The classical one is the one that everybody knows, right? It's just an emitter in a classical cavity. It's a point dipole. Mu is the dipolar moment in a local field, E, right? And the rate of interaction and energy is this G, coupling rate, energy rate, is the local field acting on the dipole. This has been coming out several times here, right? And associated to this situation, we can define several quantities of interest. The Porcelain Factor, right? How much enhancement of the spontaneous decay of the emitter is produced when you locate this emitter in the local density of states of this cavity, right? So this is connected with the quality factor divided by the effective mode volume of the cavity, and it's connected with this coupling factor to the square with coupling regime, right? The total decay here is gamma T, right? There is also important in photonics to excite this dipole, and this is proportional to the square of the local field. So these plasmonic resonances, it's here where they are very powerful, yes, trapping this field and exciting very effectively the molecule or the emitter. And very importantly, as I will show you in a second, this is kind of very common and standard concepts, the part of the total decay which is radiative, which establishes the radiative yield or quantum efficiency, also called, will establish the limitation of how much light comes out, right? And the product of this quantum efficiency by the excitation rate and the quantum yield will give you the final emission rate, right? And these are concepts that everybody's familiar with. We will use them quite a lot. The interesting thing is that when you put your dipole, your emitter here on top of a particle on an antenna open like this, we know already from the papers of Lucas and Volny and so on, that if we split this emission rate into this excitation rate and quantum efficiency that I just mentioned before, pay attention to this black line here when there is no substrate, okay? It's this situation in black here. We have a typical excitation rate when the emitter gets closer to the field, to the local field of the antenna here. But then the quantum efficiency drops after 4 or 5 nanometers, is this drop here that I'm marking here in black, because their non-radiative decay kind of starts beating the radiative yield, right? When you multiply this black by this black, the emission rate also drops and gets quenched. So you don't have light here coming out. So then a lot of people some years ago coming from tunneling microscopies were asking me, if you have quenching of light, when you have your emitter closer than 5 nanometers, why is it that we see light coming out from a tunneling junction when the tunneling junction has a distance of about 1 nanometer? It should be quenched. Well, it turns to be that when you actually put a substrate, you form a cavity, the local density of states changes completely. The nature of the local density of states changes completely. The radiative yield, this quantum efficiency in red now here, this curve in red, does not drop like here in black when the open antenna is like that, but actually keeps going up. and then the product of these two is still going up. So it turns to be that the plasmonic mode of the cavity, this bonding mode, is a very strongly radiative mode, which doesn't trigger the non-radiative part and the quenching until much, much closer distances, even below 1 nanometer. So all that we can address from classical calculations. This is a pure classical calculation that we just published last year, right, in the context of tunneling microscopy. So then you can do this tunneling microscopy experiments and address them classically: a dipole here, a molecule, a cavity which emits light like with this plasmonic fingerprint, broad plasmonic resonator, the exciton of the molecule, much narrower here. And when you put both together, like he'd already shown this, it's this a coherent interaction between the plasmonic cavity resonance and the exciton, the two-level system. And you see here this perfect funnel profile that we can address, as I say, with classical theory as a function of distance between the coupling, the cavity and the dipole, the molecular dipole. You control the cavity. If you get away, you lose the interaction, and we can reproduce this with theory, very classical oscillators, which can address the coupling strength as a function of the contrast of the funnel line, for example. All that you can do with classical electrodynamics. Is enough classical electrodynamics? Well, sometimes it is, like in the case I just shown you, but some of the times it's not. Let me show you an example of a case where it's not enough. This is a case of a two-level system that we are addressing together with Andrei Borisov in ERSE with the time-dependent density functional calculations. We provide the whole potential landscape of both the cavity here on the sides and the two-level system supporting a NOMO and a LUMO. We send light and we let the electrons evolve. And by solving time-dependent Schrödinger equation, we get the absorption of this system that includes charge transfer between the LUMO and HOMO levels of the molecule. So contrary to classical description that I just shown you before, where as a function of distance, separation distance, we would have an opening, when you include the charge transfer processes in a proper time-dependent density functional theory calculation, you see how the lower polariton is not opening anymore here. It's making something different, and it quenches the strong coupling. And this quenching is due to just the charge transfer mediated by the LUMO. This is completely missed in the classical calculation. In the classical calculation, you include damping and non-radiative processes via the ohmic losses of the interaction, right? But not the electronic damping of the charge transfer like here. So, and John Bavase will show today a poster on this, and you can ask him more details and questions about this, for example. A third aspect that we can address, cavity QED. Cavity QED for what? Well, let me show you an example on where we need this kind of nanoantenna quantum electrodynamics description. This is a collaboration with Gilad Haran at Weizmann Institute in Tel Aviv, near Tel Aviv. They have this plasmonic antenna. They locate this cadmium selenide zinc sulfide quantum dots. They are very stable. They don't photobleach so much, and they have a strong oscillatory strength. That's why they're used instead of molecules. These are the spectral properties. And it's well known that, well, they published a few years ago that when you put 1 or 2 quantum dots here, they see this opening of the strong coupling fingerprint here, right? Well, the funny thing, or the challenging thing, is the spectrum of luminescence. So compared to the scattering, or even the absorption that provides very wide split and broad peaks, the photoluminescence is less splitted and much more narrow, okay? So this is both put together. And actually, if you do this in many, many different quantum dots on both sides, you see that the split on photoluminescence doesn't change as a function of the split in dark field and scattering. So there seems to be no correlation between photoluminescence and scattering. So now this experimental group of Gilad came to us and said, hey, can you explain this? Why? Well, they actually, on top of that, have extra information, very valuable, which is this coincidence emission of the photon detection on the Hambury-Brown and Twist experiment. They can measure the second order correlation of the emission, and compared to glass, the quantum dot in the bow time changes the lifetime very little. And according to strong coupling, this should have a much, much narrower lifetime, right? So this is kind of challenges that the experimental group was posing to us, right? the photoluminescent lines are too narrow. They have a split which is independent of the strong split of the scattering and the absorption. And on top of that, the lifetime is too long, right? For that, and to address correlations and level splitting and dynamics, we go to this cavity QED description. It's a James-Cumming model, but in this case, it will be extended. This is the standard James-Cumming model, the plasmon states, the quantum dot states, the ground and the excited state. This is the quantum dot Hamiltonian, the plasmon Hamiltonian, and the interaction between the plasmon and the quantum dot via standard James-Cumming model. Well, it turned to be that this kind of model does not explain all these three experimental features. We solve these Hamiltonians in a standard way, master equation plus losses here, Lindblad operators. What we had to do, and Thomas Newman, who is now in Strasbourg, developed this model, is to include a dark state, the presence of a dark state. Quite often, this is a hypothesis, but all the experts in quantum dot tell us that these surface states and mediated phonon states present these trap surface states, which are dark. They are a little bit lower than the bright state. And when you include in this extended James-Cumming Hamiltonian, this dark state with his parts in the Hamiltonian plus the coupling, you resolve this master equation and the dynamics, you check, you obtain the spectroscopy, and on top of the absorption, the scattering, we can address the photoluminescence in this way, identifying that this fixation of the narrow states and the smaller split is connected with the dynamics of a much more complex balance of states involving a dark state. Furthermore, in the correlations, when you calculate these correlations within this framework of extended dark state James-Cumming Hamiltonian, we see a double time scale for the correlations. The one that is experimentally addressed and a much more narrower one that is not resolvable experimentally, which is very, very thin, which is consistent with this bright states dynamics, right? So I have shared with you now three different approaches, right, that are good and very good to address different problems depending on the complexity or the processes involved in the light emission or in the coupling between the light emitters and the nanocavity, right? And this is what we're going to use for different situations, right? So now, in the other 15 or 20 minutes, I want to show two messages of taking this concept and these methodologies to the extreme. The first one is to push the concept of nanocavity, nanoantenna, nanoresonator to the limit for atomic scale resolution and microscopy. And the second one is to use it in optomechanical interactions at the nanoscale, right? Let's go with the first one. We all know that this is the kind of cavity that works well. I have just shown it, how well it works. It emits light, it leaves light going out, and it interacts coherently. The excitons of these molecules interact with the cavity, right? Now we wonder, because of some experimental results, what would happen in this extra zoom area, right? And when you go to the atomic scale and you focus on the atomic scale feature of the cavity, you identify that when you send light, light gets trapped and can get trapped in single atoms, right? And so when you actually calculate the effective mode volume associated to this trapping at a single or pairs of atoms, you see that these effective mode volumes that are going to enhance the interaction with matter are below even 1 cubic nanometer. So we termed this a few years ago, 4 or 5 years ago, picocavities, because they are sup nanocavities, right? And actually the good news is that these picocavities that we calculated quantum mechanically with all full dynamics of the electrons atomistically can be reproduced very nicely with classical methods of solving Maxwell equations, right? If one addresses the boundaries of the metal atomistic profiles properly, you can resolve this atomic scale lightning rod effect, so to say. This is not resonant per se, right? But it's mounted on the resonant nanoantenna response, and it shows some kind of cascade effect at the atomic scale. The plasmonic resonance is resonant, it enhances, and then on top of that, the atomistic lightning rod effect provides an extra 2, 3, 4 times enhancement in the near field, which is very useful to enhance the interaction. This is how it works. Here I compare the local field enhancement in a profile like this, in a cavity. When it's a pico cavity, you can see here, this protrusion that now I show you that it can be described classically as far as you do the profile well, or the nano cavity without the protrusion, right? And you can see the difference in a spread of the local field in the nano cavity, typical plasmonic fields of 5 to 10 nanometers extended. Here, this is the perpendicular component, this is the parallel component of the local field, but in the pico cavity, you can see localization of fields at the sub-nanometric scale. This is going to be fantastic, not only to enhance light-matter interaction, but to scan this pico lantern, this pico light, and do microscopy, right? Furthermore, we can calculate the quantum efficiency and the emission rate of these pico cavities in these kind of situations, and we can see how, compared to not having the protrusion of the cavity, you improve also the quantum efficiency and the emission rate substantially, actually. Remember that all this goes to different powers, and sometimes an enhancement of 4, 5, 10 times here and localization can involve 2, 3, 4 orders of magnitude improvement, okay? With that, the group of Shen Xiaodong in Hefei scanned with such a pico cavity in their silver tip, a zinc phthalocyanine, and they managed to resolve with full optical excitation the fluorescence of this zinc phthalocyanine with subnanometric resolution. You see here the profile. This is as good as electronic tunneling resolution, right? How we address this? Well, and this is where Thomas Newman again comes into play. He describes the pico cavity with these classical descriptions. He puts the zinc phthalocyanine here, and he calculates with the many-body ab initio the exciton extended in a space of this zinc phthalocyanine. Okay. If you remember in the beginning of the talk, I just described the situation, the key aspects of the emission rate of this situation with a point dipole. Now we have to extend this description to account for the spatial extension of the exciton and the electronic current states profile. So we define this coupling strength, which is going to give us the main features of the emission, as the integral in space of the potential of the plasmonic potential and the density of electronic states extended in space. There's a convolution of photonic and electronic current states. When you do that and you compare it to the point dipole description, you map G, the coupling strength, by scanning the pico cavity, and this is what you get. This is the G, a contour plot, a scanning of the G coupling strength of this zinc phthalocyanine dipole is scanned by a pico cavity compared to a point dipole. You see that the point dipole is overexpressed and it loses the symmetry that the full quantum model recovers. When we compare this G, which is directly proportional to the emission rate, with the experimental feature, you can see that the resemblances and the level of resolution is completely almost perfect, right? Too good. It's you can see the 4 lobes of the phthalocyanine. You see the 4 lobes, and also the levels of coupling match very well, right? So you need both the pico cavity to have the resolution and the distribution, the spatial distribution of the electronic states to get that. Let me show you another example with another experimental group, Guillaume Schul, this time, another excellent ultra high vacuum, low temperature spectroscopist. He uses a phthalocyanine, but now a free base. This has hydrogens here, and they show tautomerization. Tautomerization is the 2 forms of this molecule, which are equivalent, hydrogens like that, or hydrogens perpendicular. And the nice thing is that because of the molecule, how the molecule is absorbed on the molecule, these 2 emissions break their degeneracy. So if you do a photoemission spectrum, this is the photon emission spectrum, this free base phthalocyanine on the tunneling junction, we can see how these 2 excitons, this one, tautomer 1 and tautomer 2, are breaking the degeneracy. They should be superimposed because they are exactly equal, but the substrate breaks this degeneracy. Forget about this for a while. This is how, when you do the scanning with your pico cavity on this, experimentally looks. This kind of shape of the emission and this perpendicular shape for the perpendicular tautomer, right? So now what Thomas Newman did is to apply the same concept to describe the rate of emission as a product of pumping, excitation, and emission. The emission is going to be this G coupling to the square, and the pumping in electroluminescence contrary to photoluminescence, is a little bit more complicated. But let's first calculate what we know. The G, exactly the same as I said before, the convolution of the electronic current density and the picocavity states. It gives the perfect dipolar emission. And now the pumping involves a little more complex process where you see that due to a transport calculation, the transport pumping rate is proportional to the HOMO orbital to the square of this free base tau-SN. When you make the product of both, the pumping rate and the emission rate, you get this funny profile, which is exactly what the experimentalists determine in their experiment, right? You can see the influence of the orbitals on top of the dipolar emission. This is fantastic. It's digging into the stomach of the molecule with light, right? So I guess I have now how many minutes? 3, 4, 5, Luis? I lost count.
You have 5 minutes.
Excellent. So the other aspect where we wanted to apply the picocavity concept was in a different type of interaction. This optomechanical interaction that in general is described as this radiation pressure of light exerted on the cavity, modifying its energy, and then producing a back action, right? And this has been done, and there are several talks in this conference. We took this to the nanoscale in a Raman process, for example, the vibrations of a molecule, and modify the plasmonic cavity, but at much higher frequency of the vibrations. And by taking concepts of a standard optomechanics with the Hamiltonian in cavity QED fashion described like that, with the bare coupling of the optomechanics, the quantized cavity field, the creation of vibrations, annihilation of vibrations. As I say, we take these concepts to the nanoscale. In a Raman process, light comes in, excites vibrations of a molecule, and the molecule sends a Stokes or anti-Stokes photons, and we can actually describe this optomechanical coupling in terms of the Raman activity and the inverse of the effective mode volume, right? So in this landscape of optomechanics, if we relate the optomechanical coupling to the losses of the cavity, we have collatons, mirrors, microresonators, some of them addressed here. We put our nano antennas, our nano cavities here. A lot of losses to the right of this axis, but very high here in optomechanical coupling because of the low effective mode volume. We actually want to even lower the effective mode volume more with our picocavities to push towards a strong optomechanical coupling. And this is what was done experimentally in Cambridge by the group of Jeremy Bamber, identifying a few persistent lines here that are driven by picocavities. Why? Because when you focus on those lines, you change the intensity, you see a quadratic evolution here with intensity of the laser power of these picocavities driven anti-Stokes emission. And this matches perfectly with our description of the nonlinearities of the anti-Stokes in an optomechanical process at the nanoscale. You need the picocavity for that, otherwise you don't get it. And in the last minute, I just make an update of what we are doing with nano optomechanics right now. Joan Sang checked directly what is the influence of assuming that the cavity is a single Lorentzian mode in our cavity QED description. And it was really nice to see that when you include the Green's function in the optomechanical description of the broadenings and the offspring effects, you change completely these optomechanical dampings and optomechanical shifts. So actually, this is something, sorry, that you can see in today's poster of Joan with collective effects, and in Thursday posters of Ruben on Thursday, right? And the last thing, it's these correlations. Again, we need all this cavity QED formalism in Raman. Nikolai Schmidt, Gesa Gieski, and Alejandro González Tudela have described this correlation, two-color correlation scheme together with us. They have applied to the nano cavity and the vibrations. And this is the kind of maps, of control maps. I don't have time to show all this now, but Nikolai Schmidt will show it today in a poster about frequency resolved photon correlations in cavity optomechanics. Very focused, with a big focus on nano cavity. And you can see the rich variety of bunchings between Stokes, anti-Stokes, anti-diagonals of leapfrog processes, generation of non-classical light, violating Cauchy-Schwarz inequality, very rich quantum phenomenology of light emission. And with that, flash of the last 2 minutes, I think I have shown you that the Pico cavities can also address quantum and correlations and nonlinearities, right? I show you how you can address with different methodologies the interaction of light emitters and vibronic emitters with nano cavities, and how by pushing these cavities to the limit of the atomic scale, we enter in the realm of picophotonics, pushing the resolution of molecules to the atomic scale and entering in a completely new regime of optomechanics. Thank you very much.
Okay, thank you very much, Javier. There is one question by Christophe Galland that says, could you use the quantum chemistry approach to assess the validity of the Pico cavity model itself by approaching a single or few gold atoms to the nanoparticle, treat it as you treat the molecule?
Yeah, well, it's, I think now I can finally turn my camera on, sorry about that. Christoph, yes, I mean, we would like to have better control of the gold atoms protruding there, right? I would distinguish two types of situations, right? The situation in ultra high vacuum, low temperature, where in tunneling microscopy or tunneling junctions, where they have so much control that in Hefei and in Strasbourg, for example, there might be other places as well, that they can just go move the tip, cross, come out, and change the resonance even with that, right? That provides a higher level of control. When you do room temperature Pico cavities with particle on mirrors, or the ones you do, or Jeremy Baumberg does, the control of approaching single atoms to molecules, you know, that is far still technologically, right? There's a lot of chemistry. We could do the calculation of the chemistry, but we are on it trying. I mean, I didn't say it, but the challenge here in this methodologies is to mix a couple of them, right? To do, for example, right, the cavity QED plus the quantum chemistry, or to do good the quantum chemistry plus the time-dependent density function and the transport. As you know, in dirty chemistry, you have lots of issues with transport, chance transfer. It's very hard to do what you're suggesting, but computationally we can try. Yeah.
Okay, I have an. Oh yeah, there is a question by Bahit that says, could you explain again the influence of a dark state on the splitting of the dot?
Yes. So the influence of the dark state is almost a hypothesis we get because we discarded anything else. Let's put it that way. We know that in quantum dots, there are dark states, surface states that trap electrons there and states there. And if you have in fluorescence this peak, very narrow, very fixed, which is independent on how much the strong coupling couples in a scattering, this means that there's some state which is more weakly coupling than the bright state that is providing this fixed narrow solution to the fluorescence spectrum. And from all the things we tried, and we tried several of them, this structure of levels, the brighter state is strongly coupled, and the darker state, more weakly coupling, is the only one that explains all the three phenomenologies, including the correlation states. Now, the question for me is, Bahit, what is the physical origin of this dark state? It's just surface states. It's the same bright state, but orthogonal in the cavity. The origin of the dark state is not so clear, but all the quantum dot studies, even ab initio, support the existence of these trap states. We don't know if those are the ones generating this fixed peak.
Okay, so thanks a lot, Javier. We have to move to the poster session. Actually, before there is a break, this is a time that we need, actually David needs, in order to set up the breakout rooms. So please don't leave the session. You don't have to leave this session, but in something like 15 minutes, the breakout rooms will be open for you, so you can enter them. In order to select the posters, we remind you that you have the list of the posters now in the chat. So if you click there in the link in the chat, then you can find the posters today, and then you can go to the breakout rooms, as I said, in 15 minutes. So I see you there later this afternoon. Okay.